Assalamu alaikum dear students. Today's lecture is about the sedimentation, coagulation, flocculation and its design aspects. Earlier we tried to explore what is the theory of these topics, and we try to understand the basic phenomena of these topics. Now in this lecture we will be focusing on the design aspects of sedimentation. Earlier we studied that sedimentation has different types, but today we will only focus on the designing of a plain sedimentation process in which the discrete sedimentation is taking place. The other types will be followed that will have a different designing parameters, but today we will only talk about the plain sedimentation and its designing. As in discussed in the previous lectures, the sedimentation is simply the settlement of all the suspended particles which are existing in the form of colloids, and then we tried to find out what is its implementation in our designing in our wastewater treatment plant. Then we also try to find what is the theory, how this sedimentation process is actually taking place. Normally the three types of sedimentation describes what are the possible settling phenomena. So then based on those we are going to further find out what should be most appropriate for our design of wastewater treatment plant. And then when we talk about treatment plant, we are actually talking about the designing of all the sedimentation or settlement tanks which are actually going to facilitate these processes. These processes are normally taking place in the tanks which are called settling tanks or sedimentation tanks. Then what kind of phenomena is going to be followed in those procedures will all depend upon the characteristics of the wastewater and what kind of parameters we are going to focus. While we are talking about the settlement of different components which are present in wastewater, we will be actually talking about those discrete particles which are having their own identity and which are existing in the form of colloids and suspended form. Then we will talk about their dimensions, their sizes, their volumes, their densities, and then their settling phenomena. So starting with the settling tanks, we will be just revising the theories and then operation and then design. We have already talked about it in the previous lecture. Today we will not be going into the details of these topics. So these settling tanks, which are also called sedimentation tanks, and basically the purpose is to settle down the coarse particles, and then after the settlement all those coarse particles will be settled in the form of sludge, and then the clear water, the clarified water will be passed on to the next chamber for further treatment. And in this settling tank, all the sludge will be settled down, and which can be removed by the different procedures, for example pumping them, and for example removing them manually. So gravity is settling, the particle will tend to fall to the bottom, forming a slurry at the vessel base. For dilute particle solutions, two main forces enacting. First of all is the gravity, force, and then there is a drag force, that is due to the motion of the particle through the fluid, which is actually resisting the movement of the particle towards the bottom. So both these forces will be actually balancing. We will be talking about it shortly. So some of the definitions, I think it is kind of revision. We have already gone through these definitions, so please just revise them. So these are the procedures which will be covering our sedimentation, which include the gravity separation under the own load of the coarse particles, then filtration through screens and granular material medium, then flotation, which is will be removing the matter from the top layer, or any similar procedure. So settling basins have normally the best option for us for the treatment of wastewater, because majority of the wastewater components can be simply removed under their own load, and these coarse particles can settle down due to their density. And then however, we can increase these densities, and then we can coagulate these particles to join them to make flocculates, and then this combination, this flocculant will actually have a higher density, and it will facilitate in the downward movement under the gravity. At the same time, there is another force which is called force of buoyancy or drag force, which is acting in the opposite direction. Both of these forces are actually balancing each other, and it will be important to know which is going to dominate. And then because of that, and we will find in Stokes law, which will be defining the movement of particles, that the dimension of the particle is very important, the diameter is important. So when we increase the diameter, when we increase the size, actually we are increasing the tendency of the particle to settle down under its own load and due to the gravitational forces. Some of the advantages are described here, then we have disadvantages. Please go through these. And then so the plain sedimentation is actually, it is a separation or removal of suspended solids from water by gravity force. If specific gravity of the suspended particle is more than 1, it will settle with a certain velocity. Therefore, if water is allowed to remain in a basin or tank for a certain time, the suspended particle will settle and reach at the bottom of the tank, and finally the water will be clear. The sedimentation tank may also be referred as sedimentation tank or settling basin or settling tank. So it refers to what are the principles of sedimentation. In this case, we are only talking about the discrete particle settling, how, which phenomena is going to dominate, how we are actually removing these particles. It is described, and it refers to the sedimentation of particles in a suspension of low solid concentrations. It's only possible when the level of contamination is not high, the concentration of contaminants is not high, the particles are not so closely bound to each other. So every particle is behaving in its own capacity, in its individual phase, so that its own weight is the only force of which is going to help it removing from the tank, from the fluid. So particles settling as an individual entity are and there is no significant interaction with the neighboring particles. It is only possible when the concentrations are low, but with the high concentrations we have different other methods which will be taking part as well. So just for a reminder, we have earlier talked about the zone settling, in which the denser particles are actually making a cluster, and it is moving downward due to its load, high concentration, and due to its high density, and everything coming in its way will also be moved forward towards the bottom of the tank and making it a part of the sludge. Thus that those discrete particles will also be removed with this zone of highly concentrated and densely clustered particles. So there are certain laws which will be governing the movement of these particles, and most important one is the Stokes law. According to this Stokes law, this is the equation in which you can see that v is the terminal velocity, and then we have rho, which is first of all it is about the mass density of the particle, then the mass density of the fluid. There should not be s as mentioned here, and then we have the acceleration due to gravity, it is also mu. So then we have absolute viscosity of the fluid. So here it is the another form of this equation in which specific gravity of the particle is mentioned. When we are going to talk about the designing of this sedimentation tank, in that case we will be talking about all the flow which is coming in through inlet and then moving out through outflow zone, and then at the same time we will also consider the volume which is staying in this whole volume of the tank, and what it is going to represent is the settlement of the particles from this inlet point to the outlet point, and in between these 2 points we can observe the settlement taking place of the particles and under the settling velocity. So how we can determine the settling velocity? We have already checked it in the form of Stokes law. So then the design of sedimentation tank is based on the ideal sedimentation basin. There will be some assumptions which will be important for the designing of this tank. First of all is the complete mixing and uniform suspension at the inlet zone, then uniform horizontal velocity in the settling zone. There is no flocculation considered in this case because we are only talking about a discrete free settling. While talking about the flocculation, we have already a phenomena which is about the higher density levels of the particles due to the flocculants. Particles that reach bottom are permanently removed. It is also an assumption. So just have a look at this diagram which is explaining all the parameters of the designing. We are having first of all an inlet, and then on the other end you can observe there is an outlet, and in between these 2 points there is a main volume of tank in which the horizontal flow will take place, and then the fine particles will be having its movement from at the top layers because there will be lesser settlement, while the coarser particles will have a tendency to settle down in the zone as mentioned here in this diagram. So at the same time you can see the flow path through these baffles, which are baffle walls, and these are actually provided in the inlet zone. So this is for sludge removal. Here is some explanation about the velocity which is going to take place. and while we are having a flow q flow rate coming inside the tank in the form of q is going to be taken all the way to the outlet flow, where we will be getting clarified water. Most of the particles which will be having a settling velocity will settle down in the initial zones, and other particles which are lighter in size with lesser densities will remain apart in the fluid and will sustain their place in the top layers of the wastewater flow. This is the plan view of the tank. So then we have another term which is called surface overflow rate. So while we talk about the particles which is entering the basin, it will have a horizontal velocity which will be equal to the velocity of the fluid, because that particle is moving along the fluid. So that velocity will be explained in terms of q, which is discharge, will divided by the area. So what kind of area we will be including in this section? It will be width of tank and depth of tank. So this width and depth will actually be giving us the whole area along which the flow of water is taking place. Just consider that in this case the length of the whole tank is not considered, because we are only explaining it based on the cross-sectional area through which the whole discharge is taking place, because this discharge is taking place perpendicular to the flow of the wastewater. In this case, the perpendicular area will be explained in terms of the depth of the tank as well as the width of the tank. It will not include the length of the tank, because the movement is supposed to be perpendicular to the area. So that area which will be only facilitating the movement of the entire volume of the wastewater will be included in this calculation. The other velocity is the settling velocity, Vs, of that particle which is defined by Stokes law. If a particle is to be removed, its settling velocity and horizontal velocity must be such that their resultant V will carry it to the bottom of the tank before the outlet zone is reached. So this is very important, because it will explain which velocity is required for the removal of the particle from the flow, and which velocity will be facilitating the downward movement of the particle. In this case, if you observe, there are two velocities which will be involved. First of all is the horizontal velocity, which is actually equal to the flow of our wastewater in the forward direction towards the outlet. At the same time, there is a settling velocity which is only influenced by the Stokes law, which will only be including the gravitational force. Actually, it is having a net force, not only gravitational force but also a drag force. So the net force which will be acting on it will facilitate the movement of the particle to the bottom. So that net force will be used in the Stokes law. Now this force which is described here will have a resultant. So first of all, we have a horizontal velocity, then we have a settling velocity, and in both the cases we will be having a resultant vector. If that resultant vector is falling in the sludge in the disposal zone which is at the bottom, and if that resultant is falling in the up to the end, which is end of the tank. In that case, that particle will be removed from the wastewater. Otherwise it will keep suspended in the wastewater. Thus if it will keep suspended in the uh, in the flow, it will be not removed from the wastewater, and there is a possibility that it can shift itself to the next zone. So in this case the resultant must be larger, and it should facilitate that it must be within the range of that sludge zone. So if you go through this, and then if a particle entering at point A at the top of the basin is so removed, all particles with the same velocity will be removed. Considering the slope velocity vector from A to F and the dimensions of the basin itself, we can write. So based on this theorem, uh, you can observe that we are considering two triangles similar, and we are going to match their equivalent sides. So by doing this, you can observe that first of all we have a settling velocity Vs, and ratio, we are taking its ratio with the other velocity, which is horizontal velocity. And then on the other side we are taking the length of the dimension of the side which is representing that velocity. So the velocity, settling velocity, is taken by the depth h, while the horizontal velocity is taken by the length L. So we are comparing the both the triangles, so we can write it in this form. By writing this in this form, we are going to simplify this formula in the form of Vs, which will be equal to V into H divided by this L. Now here you can observe that the this velocity, which is representing the horizontal velocity, we have already described it as a flow per unit area. So and that area is cross sectional area. So flow is expressed by Q, and area, cross sectional area, is expressed by the depth multiplied by the width. So in this equation, by simplifying it, we can get this Vs is equal to Q over B into L, and B into L is giving us the horizontal area of the tank, or plan area. It defines the surface overflow rate, which is numerically equal to the flow divided by the plane area of the basin, which physically represents the settling velocity of the slowest settling particle, which is 100% removed. So this is the diagram which is representing. We have taken the dimension AF, and at the same time we are also taking this AC, which is representing the H, and then we are also taking the length L, and then we are comparing the two velocities, settling velocity and the horizontal velocity. So those particles which settle at velocities equal to or greater than the surface overflow will be entirely removed. Then we have a detention time, which will be representing how much time that particle must stay in the tank, and it is defined by volume over discharge Q. So volume is H into L into B. If you put these values here, we can get it like this, and then simplifying it, we are further going to have this H over surface overflow runoff, and then actually this is representing the settling velocity. So denser the and large particles have a higher settling velocity, and then we can observe that uh, now some of the design criterias which are based on the experience and continuous designing practices. It implies a horizontal flow pattern with the flow along the long axis lengthwise. Such a flow pattern minimizes the effect of inlet and outlet disturbances. Then the length of these tanks can be 90 meters, but commonly it is used as 30 meters. Uh, Width of the tank should not be more than 12 meters and should not be less than 1 by 4th of the length. These are some of the design parameters. The flow may enter, now this is something about the circular basin, and then the flow may enter at periphery or at center. Average detention time is greater in peripheral feed basins. Then there are some requirement of the blades for the cleaning purpose of this the circular tanks. So in this case it is only possible if we are considering the design of circular tanks, and the diameter is supposed to be 30 meters. And at the inlet and outlet, again some careful design of inlet and outlet is important to assure a reasonable performance of sedimentation tank, because we need to control the flow, that is Q, and based on that Q we are going to design our tank. Then this inlet is also provided with the baffle walls, because there is a smooth flow is required, uniform flow is required to be maintained. And furthermore, if we provide the baffles, it increases the tendency to settle down, and it creates a turbulence and facilitates the discrete settling of the particles. So then at the outlet, again we are having some weirs which will be facilitating in the final discharge of the effluent. These are some of the diagrams. You can go through these diagrams, and these are the design criteria for sedimentation tank. Normally the detention time is supposed to be between 3 to 8 hours. Then SOR is generally 20 to 40 meter cube per meter square per day. Then depth of the tank is supposed to be 3 to 6 meters, where over flow rate is 250 meter cube per meter per day. These are some of the diagrams. We have already talked about it. These are some of the examples which you should try by yourself, and then we can talk later if there is some problem. And so coagulation is actually a continuation of the sedimentation process, and in this case it is not for the plain sedimentation, but it is actually for the formation of the coagulants with the help of the use of some chemical. So it's a chemical technique acting directly towards destabilization of the colloidal particles. And then what are the colloidal particles? These are the particles which are in suspension. The settling velocity of finely divided and colloidal clay are so small that removing them in a settling tank is impossible. And then it's therefore necessary to coagulate the very simple particles into larger ones, and then help them remove. The chemical Chemicals commonly used in coagulation include alum, ferric chloride, and ferric sulfate, sodium aluminate, ferrous sulfate, and lime. These are the coagulants. And classification of the suspended particles. Here you can see these particles and their sizes. What is the coagulant dosage which is required to be designed to be optimized? It generally expressed as grains per gallon, and 1 grain per gallon is actually equal to 17.1 milligrams per liter. So the optimum dosage of coagulant is found by a test known as jar test. I'm sure you are quite well aware of this test. So first of all, we need to place 1 to 2 liters of sample in 6 beakers, then prepare a solution of coagulants of such a strength that 1 ml contains 10 milligrams of coagulant. Then add desired amount of coagulant and lime to each sample and shake it vigorously, and then flocculate the sample for 20 to 30 minutes at 30 to 40 revolutions per minute. Then let the sample stand for 30 minutes. Take the clarified water for analysis. We need to determine the pH, turbidity, alkalinity, and CO2, and etc. some other. So based on these findings, we can best choose what is going to give us the best of the performances. So the dosage which was found to be the most optimum one is going to be recommended for the usage in the tank. Similarly, there is some effect of pH on coagulants. So for example, alum is going to have a better performance at 4 to 7 than ferrous sulfate 8.5 and above. Ferric chloride works at 3.5 to 6.5 and above 8.5. Then we have ferric sulfate. Its range is 3.5 to 7 and above 9. So that's all for today's lecture. Please go through it thoroughly, and then we can discuss later. Thank you very much.